So I would like to talk about another algorithm which relies on patches as its substrate and which also beautifully uses this idea of letting the data speak for itself. Again, it's a super simple algorithm. It was published in 2005 and in a journal in 2007, and it has now been superseded by algorithms that produce somewhat better numbers in the benchmarks. But I would say if you take into account ease of implementation and quality of results, probably this is still the best trade-off that you can get. Again, it's a very, very simple algorithm. So non-local means, and the image explains the principle. We have a patch P that we want to denoise. There is a patch P that we want to denoise. And this patch P will be explained as a weighted sum of itself and many other patches in the image. And shown in particular here are two examples, like this one here that has very similar content, and that one there has very similar content. You know, it all shows the same vertical bar in the background. And then there's another patch that looks very different. So the similar patches should get a high weight in this linear combination. The different patches should get a low weight. So what this algorithm is all about is it is about exploiting the self-similarity that we see in most natural images. This is a common feature of natural images that, you know, in principle, you could conceive of an image where, you know, in one patch you have the edge of a bridge, and in the adjacent patch you have an eyebrow, and in an adjacent patch, you know, you see a technical part, but that's not what real images look like. Real images always have, on the one hand, some degree of smoothness, and on the other hand, there is typically in images the kind of repetition that's sketched here, or if you look at, you know, let's say where the head here transitions to the face, there are also a couple of patches that look the same, and so on. The way this is done is that every pixel in an image is explained as a linear combination of all others. I put all in quotation marks because for computational reasons you don't really use all, but in principle you use all, and the only thing that matters is the weight that they get in this linear expansion. Pixel. But the weights are obtained from the patches. So in the notation of the paper, we have a noisy image V, which is a collection of pixels here. Capital I is the domain. And the non-local means estimator based on a noisy image V at location I is the weighted sum of all pixels. where this weight will be derived from patches. Now what we have here is just a specific instance of a so-called Nadaraya-Watson kernel smoother. And I'm taking an image here from the very good book by Hasey, Tipshirani, and Friedman. Let's focus on the left-hand side. First, this is a one-dimensional example. So I have one feature X, and I have one response Y that I'm trying to approximate with a function f hat of X. You see here a blue line from which the data was generated, and then you see all these random observations. And shown in green is the nearest neighbor estimator. We talked about nearest neighbor, we talked about k nearest neighbor last time, and we talked about k nearest classification. So the aim was to predict, in the example that we talked about, one of the digits. We wanted to predict the class 0 or 1 or 2 or 3 or up to 9. Here we want to predict something continuous, so this is a nearest neighbor regression. Now I could in principle use a one nearest neighbor regression, which I would obtain by simply sorting all my pixels, and my one nearest neighbor regression would look something like this. I think you're getting the idea. So I'm always connecting the pixel, I'm sorting my observations according to X, and then I always use the pixel which is closest in X to make my prediction. Now that clearly, is not a useful estimate. So what you can do instead is you can take you could, for example, take always the 10 nearest neighbors, or you could take, and I'm not sure which of these two algorithms is shown here, you could take a fixed search window, which is here indicated by this yellow box. So if I want to make a prediction here at x0, I would take into account all the observations in this corridor here and would take their average. So if I take always the, something like the 20 nearest neighbors, then this would be a 20 nearest neighbor regression. If I fix a radius or a width of the corridor, I could fix this to have a width epsilon, then this would be an epsilon nearest neighbor regression. In either case, I'm not sure which of these was used. You see that there is a green line in this plot, and this green line shows you this interpolation. And you see maybe that it's a pretty jagged line. Okay, there's my interpolation. It's a pretty rough estimate. Now it is rough of necessity because as I move my query location x0, if I move it a little bit to the right, then my data selection corridor will move a little bit to the right, and new observations, they are either within my corridor or they are not. So I shift this corridor, and whenever a new observation enters my corridor, my estimate jumps up or down a little bit, but this jump will always be discrete. Now, having such a jagged estimate is not nice, and you can also argue that if you have such a corridor, that the points which are closer to your query should get higher weight than the points which are further away. And that naturally leads to the suggestion of having not a 0-1 weight, but of having something that's smoother. So if I show the weight function of the previous image, the weight to make a prediction at x0, in the previous image we had this weight function which was either exactly 0 or exactly 1, so the box function. Here instead, something smoother is used, something which gives 0 weight to points which are too far away, and then gives a weight that increases and decreases, and so on. This is just an inverted parabola, an inverted truncated parabola, which is a fancy name. It is the Epernechnikov kernel. It has this name after a statistician who proved that this kernel has particularly good properties in kernel density estimation. So now, as I move my query point, the points which just about enter my search horizon, they have low weight, and the closer they are to the query point, the higher weight they have, and so on. And because my kernel is no longer discontinuous, my kernel now is continuous, here with regard to this 0 line. Because my kernel now is continuous, so is my estimate. It inherits this continuity. And this is now shown by the green line, which most people would argue and agree that it's a nicer fit than this jagged line that we saw here. So this is the Nadaraya-Watson kernel smoother, and the one thing that you need to do is you have to make sure that there are some regions where you have more data points than others, so you need to normalize for the weighted number of data points that are actually in your prediction window when making a prediction. So using the notation that I've I'll show that in a minute. So we need this normalization, is the only thing I want to say. Okay, so what is this to do with image denoising? This is what we had in mind originally. Again, this viewpoint is taken where each patch is vectorized, and each patch becomes simply a point in a high-dimensional feature space. So let's say if we take these patches to be of dimension 7 by 7 pixel, then it means that each patch is a point in a 49-dimensional feature space. In these examples here, we had one-dimensional feature spaces. So we had just, one feature X and one thing that we wanted to predict. If we want to denoise gray value images, we still have just one quantity that we want to predict, namely the gray value or the intensity at the pixel. But now we no longer have a single feature, but we have 49 dimensional data. However, I can still use the same principle. And what the non-local means algorithm proposes to do is to use a kernel similar to the Epernechnikov, but they don't use the Epernechnikov, but they use the Gauss kernel instead. So W, this weight function, Wij, in their paper they don't put the 2 in the denominator. And here comes the normalization. So as a consequence of this normalization, we have that the weights are all between 0 and 1. and that they sum up to 1. Now we still need to talk about this distance. In this example here, distance was simply the Euclidean distance between 2 points, and they use, well, depending on the paper you read, either the Euclidean distance or a weighted Euclidean distance. So this distance ij between 2 pixels I and j is given by writing this in a continuous formulation, even though we have a discrete image normally. So now, you know, I is a 2-dimensional vector, and t is also a 2-dimensional vector. Okay, now comes the weight function. This weight function could be just one which is 1 inside a patch and 0 outside. What the authors use in their paper is instead a Gaussian. So we have high values close to our query or to the central point and lower weights further away. So I'm writing G here for a Gaussian with standard deviation A. So the size of this Gaussian would be given here by A. But that's a minor detail. And as I said, people use different implementations, and sometimes they use the Gaussian, and sometimes they simply use the box weight function, which is 1 inside and 0 outside. Yeah. It's a different. Why do I apply the Gaussian twice? The first here has to do with tapering the distances. So let's say, you know, I have my original image. Let's say there are 2 patches that I want to compare. So I have accounted for the shift that lies between these 2 patches. And now one possibility is to sum up the squared gray value distances for all pixels. And the alternative is to say, I want to give a higher weight in the center than at the periphery. And this is what I try to indicate with these equi-contour lines of the Gaussian. So this is what that Gaussian here is used for. The other Gaussian is in this different space. The other Gaussian, you know, is in this space here where I have many points and I want to weigh them according to their similarity. So this is a measure of the dissimilarity itself, and this is the weighting according to those dissimilarities. This second formula here says that I am always comparing parts of the picture. You know, perhaps it's easier to here not use the Gaussian, but to use the box function. So the box function, that's the one here, it's 1 inside a rectangle and 0 outside. So the similarity between pixels I and j depends not only on pixels I and j, but also on their surroundings. This is what the integral here says. And the surrounding can either be a crisp one, 1, 0, a box function, or box kernel, or it can be something smoother. so that the locations close to the query pixel get higher weight than those that are far away. But the choice of this weighting function is arbitrary, and the choice of that kernel here used in the Nadaraya-Watson smoother is also arbitrary. It's just good if it is smooth, because then the estimate will inherit this smoothness. Yeah, so what you're saying is that the Gaussian, only decays to 0 but never becomes quite 0, and that better results might be obtained by using something like a B-spline or so, which has a finite support and which is exactly 0 afterwards. No, the Taylor expansion wouldn't do the job, because then you get funny negative contributions. Yeah, okay. So there is some freedom in choosing this kernel here, and actually for density estimation, this one is better than that one. So density estimation, kernel density estimation, one of the few places where the Gaussian is not the perfect thing, but where other kernels do better. Okay. So let's scroll out a little. We have now a means to compute the dissimilarity between 2 points I and j, and this dissimilarity depends a little bit on this, or depends on the surroundings of these 2 pixels or 2 locations I and j, that can be plugged into a weight function. So there are some points in the image which are more distinct than others. If we go back to this image here, the bar here at the vertical bar in the background, there are very many patches, and they are of course overlapping also, that essentially look the same. And then there are other places like I don't know which ones, but let's say this place here where we have a corner. There may not be, this corner might be found again somewhere in the feathers of the hat. Also, the nostril looks unique to us, but actually the nostril may appear also somewhere in the feathers of the hat. But even so, there are some patches in this image which will have more close neighbors than others. And this is why we need to normalize here. This is why we need this denominator to account for that. And then these weight functions are used here in a simple linear combination. And in essence, this is it. Now, as I've described it, this would be very slow, and you want to speed it up. But anyway, it works pretty nicely, as I want to illustrate in terms of these images here. So there's the original image, which was made noisy. So the noisy version is not shown here. And then you see the result here of filtering this just with a spatial smoothing kernel. And the image shown here is a difference between the smoothed version and the original image. And you see that this, well, now all the edges come out, meaning the edges were lost in the smoothed version. This is if you use anisotropic filtering instead, so you still see a lot of structure here. In the bottom left is when you use total variation, another important method. It still leaves a very structured residual. There's a method I don't know. And here in the bottom right corner is non-local means. And you see that there is essentially no structure left in the image, which is good. In the bottom you have a noisy version, and the results that you get from Gauss filtering, from anisotropic smoothing, which makes for some interesting artifacts, because in such anisotropic smoothing, you always have to decide if there's a local, direction of preferred orientation. And for example, it looks like that at this position of the head, the edge strength was not sufficient. So the head starts to bleed out into the hair, whereas in the other locations it was retained. Then there is again a total variation, another method, and there is non-local means. And to go from the noisy image here to that one there, there's no mean feed. I think it's a very nice reconstruction. So I have one more comment, namely talking about this dissimilarity here. Finding this dissimilarity is a kind of chicken and egg problem. Because we need to remember that the original image is quite noisy, or can be quite noisy. So we have the question of which patches are actually similar or dissimilar. And to answer that reliably, it would be good to have a noise-free image. But we're doing the whole thing to obtain a noise-free image. Okay, so this is a bit of a circular argument here. Even so, it can help to use some simpler denoising strategy first before computing this dissimilarity. So it can help to compare denoise patches. Again, the whole point of the entire method is denoising, but there are also denoising methods, wavelet based and other, that are independent of the image that you're looking at, and you could use one of those, or at least two people had the same idea simultaneously. So there is Tasdijan at ICIP08, and there is another paper by Orchard and colleagues at the same conference, who both suggested to first project the patches to their principal components. So project the noisy patches to the principal components first. So I have not explained what principal components are. What you do in essence is you take your 49-dimensional point and then you project it to, let's say perhaps just the 6 most important dimensions, where most important has a certain well-defined meaning. And you kill 2 birds with a single stone. Man schlägt 2 Fliegen mit einer Klappe hier. Namely, on the one hand, this gives you improved results, and it gives you speed up at the same time. Simply because computing distances in 6D is faster than computing distances in 49D. All right, any questions? Could you implement it now? No, I see a shaking of heads, so please ask. How do I map or match? So we start with one pixel for which we want to make a prediction. And to do so, we compare this pixel to all others in the image. But if we just use the gray value of this pixel, it would not be very informative. So what I use to compute the similarity is either Gaussian or just a Gaussian weighted, or just a patch. So it means I take the 7 by 7 pixels around this pixel, which is one point in 49-dimensional space. And now I compute this in principle to all other patches in the image which are overlapping, to see how close they are in this 49-dimensional space. And this distance in 49-dimensional space, it does not depend on how far apart they were in the original image domain. It only depends on how similar the patches are. And this patch similarity or dissimilarity is then transformed into this weighting function. So for example, a patch is always similar to itself. And let's say if there was just a single other patch in the image which was very similar to this one, and all the others were dissimilar, then the patch itself and the other similar patch would get a weight of 1/2, and all the others would get a weight of 0, roughly. Whereas, if you take this example here, this patch has very many different patches. Let's say we find 100 patches that are equally similar and all the rest are dissimilar, then each of these would get a weight of 1/100th and the rest would get 0. And now normally similar or dissimilar, it's not a binary thing, but we use this Gaussian function to achieve this weighting. So we use this Gaussian function here to argue what I consider still as similar or as dissimilar. And then the denominator of this expression, I simply need to normalize to guarantee these properties here. So in summary, to make a prediction at a pixel, I look at all other patches in the image, I compute the dissimilarity, I weight the contribution of the others according to those dissimilarities, and then, given these weights, take the weighted average that you saw in this equation here, take the weighted average to obtain my final prediction at the original pixel. Now, to do this in practice, some speed up is needed, so I don't really consider all patches, or I use an implementation using the FFT to make computations faster. But I didn't want to talk about speed ups here. I wanted just to explain the principle. Okay, so you can either impose, and now there are many implementations possible. You can either impose a hard limit, like I never want to take an average of more than 100 patches, or you can, what was the other part of your question? Yes, so in practice, one does not search, you're right, in practice one does not search for all patches, but I think in the original paper it says we look at all 7 by 7 patches, but only in a 21 by 21 neighborhood, something like this. But these are just heuristics to make it faster. So they do not change the principle of the algorithm. More questions? So question, does it also work on curved edges and such? probably you would have. So actually, even when you have curved edges, 7 by 7 pixels is not very many. So if we look at this hat, for example, the direction here is somewhat different from the direction there, or the orientation is a bit different. However, if we're only looking at a 7 by 7 patch, then they may still look reasonably similar. So the only kind of image where you really have no dissimilarities or no similar patches at all is in a white noise image. But then in a white noise image, what do you want a denoising algorithm to do? So it's actually, very simple and yet quite powerful. So of course, in a discrete image, we don't have an integral, but we have a summation. And the V's here are really, for gray value images, these are just the intensities at those locations. Yes? Yes, T is a 2-vector, so it indexes the location in the image. So we have just 5 minutes left in this hour, which is a bit short to start the next topic. So let's have a 15-minute break before we switch to a method called BM3D, which follows the same basic idea, but delivers even better results. However, it starts to be a little more engineered, and I will explain it after the break.